Modern science and philosophy, are they radically opposed? Last lecture we came to the conclusion that they're not, and we're going to see that more now, but this is a sort of modern dichotomy that's in our cultural mindset, and that is there seems to be this opposition between philosophy and science, between Galileo and St. Thomas on the one hand. I want to start by using a phrase that I break down into 5 pieces, a phrase of Hawking. The physicist, a well-known physicist that I've already mentioned, Stephen Hawking, that has the muscular disease, is also a profound physicist, and he's, in his book Brief History of Time, made a statement that I parse this way: 5 different things, and this allows us to investigate and find the place of the specialized sciences in the place of philosophy, and in general put everything in its proper place. Modern science is radically different from the science that came before it, says Hawking. Galileo was largely responsible for its birth, that is the birth of modern science. Catholicism, at least in some ways, and at least or at Galileo's time, intrinsically opposed to science. Galileo was the first to argue that man, this is a spelling error, man, could hope to understand how the world works. He was the first to argue that you could understand it by observing it. This is what Hawking claims. And this will serve as our introduction to this dichotomy that's often brought up between philosophy and science. But the immediate answer comes to us: no, philosophy and modern science are not opposed. The situation is very complex. This will resolve all Hawking's points and explore our improper knowledge and try to turn it into proper knowledge, which is the role we've chosen for ourselves right from the beginning, and when we recognize that a lot of the things that we think we know are really faith based on authority. To find out how they fit together, we need to look at both philosophy and modern science. We have already said that you abstract our knowledge from the sensorial knowledge. But there's 3 levels of abstraction. The first level leaves behind the least, and this we call physica, the Latin for physics. If we want to use the word physics, we should use physics in the wide sense. And this sentence is actually wrong. What I mean to say here, physics in the wide sense is what we'll call physica. Physics in the restricted sense will reserve for modern physics. So the word physics, when we just use it by itself, will usually mean modern physics. We'll say physics wide sense or physica when we mean the broader thing that Aristotle and St. Thomas mean. And that is this first level of abstraction, the study of changeable being, the study of form-matter composites. And at this first level of abstraction, we leave behind only particular matter, not general matter. So we abstract, for example, from this particular flesh and blood, but we keep the general idea of flesh and blood. That's sort of the least level of abstraction that you can do. That's the first level. The second level is called mathematica in Latin. Of course, there's Greek equivalents. You'll find them in the book. It leaves behind all of the sensible aspects of things and keeps only the quantitative. So remember the list of Aristotle's categories. There is quantity, quality, and then relation, and so on. Quantity is the first accident. It's the bottom of material things. And mathematics leaves behind everything but it. We call that first accident, that quantity, which is extension, universal quantity. And remember that images will be particular, but we will use images in mathematics as we'll look back at things that have these quantities. And quantity, what is quantity? How do we get that? Well, we get it, first of all, you look at a table, for example. In the table, we can feel the extension. We can see the extension. Or sound. You might hear a sound that's emanating from there and there, and you get the idea of extension. Now, quality is known first. I hear the loudness of the sound, or I see the color of the thing. And through the color, I get to know the quality. If I couldn't see anything, then I couldn't see that part of it's there or part of it's there. If I couldn't hear, I couldn't hear that part. If I couldn't hear the sound, the quality that's impinging on my ear, if I couldn't hear that, then I couldn't then deduce, or not deduce, but abstract quantity. So quality brings us quantity. So for us, quality is the first thing we know, but in the thing, the quantity is the first accident. And what's the difference between quantity and quality? Well, it's an important distinction between the quantity and quality. Quantity, if I take two different quantities, I can put them together and get a third different quantity. That's not the same as with a quality. And you can take an easy example of, say, say you have a mediocre mathematician. So you get two mediocre mathematicians. Say you get a room full of mediocre mathematicians. Does that mean you get an excellent mathematician? Does a room full of mediocre mathematicians make an excellent mathematician? Do you get the results of an Euler or a Gauss by getting together even an infinite number of mediocre mathematicians? Of course not. The quality cannot be gotten by adding pieces in the way that quantity can. And there's other examples. For example, you can't heat your pizza by getting more and more snowballs. The quantity of snowballs doesn't add. The quality of the temperature doesn't add. Now in quantity, there's no more or less. You can have a more or less intense quality. You can have the quality of being a better mathematician or a worse mathematician. But in quantity, there is no more or less. For example, a friend of mine used to walk around saying, jokingly of course, that for large values of 1 and 3, 1 plus 3 equals 5 for small values of 5. Of course, that's nonsense. There's no large and small values of those things. Quantity does not admit more or less. Quantity is a study of things that can be conceived without matter, but can only exist in matter. So I can conceive of a circle without matter, but it can only exist as a property of something, as an accident of something. Mathematics, though, is closely associated with beings of reason, we saw. But they're always reductively real, maybe remotely reductively real, but they're always reductively real. That is when taken as a succession of things. We saw -2 can be divided into the operation of taking away and the mathematical being, real being of 2. The other thing about mathematical abstractions is that they're idealizations. A circle doesn't exist once it's in the matter. It has a particular hardness shape that only approximates a circle, and we get the idealization from the abstraction. This whole arena, the famous and in some circles, philosopher Jacques Maritain calls the realm of the mathematical preter-real to help to describe the world that is composed of these sorts of objects. Jacques Maritain, by the way, I consider him to be the best philosopher of the last 2 centuries. No holds barred. He's done incredible work that still needs yet to be recognized, basically using the work of Aristotle and St. Thomas. The third and highest level abstraction is that of metaphysics. The metaphysics, you leave behind all material aspects of a thing and consider being as being. St. Thomas calls it separation because by a negative judgment, you're leaving behind all these things associated with material things. So they can exist in matter, but they don't have to exist in matter. And in this way, you can talk about everything in a general way, and metaphysics can address everything from a standpoint of first principles. So for example, angels would be an example of something covered by metaphysics, because you're not just talking about something that has to exist in matter. Other examples are the idea of quality or potency, substance, causes, and the transcendentals. All those things do not necessarily have to be associated with matter. And that's the key, not necessarily having to be associated with matter. All first principles get their full formulation in metaphysics, when you finally consider their full being as being. So we have 3 levels then. We'll come back to these, but to help you kind of get used to them, I'm going to look at them from another angle. You can look at them from how their conclusions are verified. In Physica, the study of changeable being, the first level that leaves behind particular matter, only leaves behind particular matter, being is resolved in the senses. In Mathematica, the conclusions are verified in the imagination by the use and manipulation of things in your imagination. Metaphysics, being is resolved completely in the mind. So here we have in this world, remember we said this referential world whereby you become united with the thing, whereby I become the coldness of the glass. I become the dogness of the dog. There's an idea by which I'm united to that thing. I take on the form of the thing as its form, not as my form, but I don't lose myself. So there's this other world, this world of the intellect. And this world is subdivided into physica, material being, the study of changeable being, form, matter, composites, and then the world of quantity, universal quantity, which is subdivided into arithmetic and geometry and also analysis now. And metaphysics being, those are the three levels. And we see the typical things. Aristotle looks at all of them. Descartes looks at just the mathematical. Einstein, for example, in his theory of relativity, looks at the physical, but reflects as reflected only in the mathematical. So for example, in his theory of general relativity, it's all about the physical, but what is its form? What does it take in its descriptive form? What mode of explanation does it use? It uses the mathematical mode. So he looks in there and glances off, penetrates into here to see the mathematical aspects of the world. Now we're ready to lay out all the sciences. Sciences, again, used in the wide sense of scientia, Latin meaning knowledge. Or else we could call it philosophy in the wide sense, love of wisdom in the wide sense. So the sciences then, in that wide sense, are divided into three areas. The pure sciences, which is the study of truth as truth. The applied sciences, which is truth in action, the study of how you should act and why you should act and when you should act. They're also called the practical sciences. Or the methodological sciences, which is the study of the human tools for obtaining truth. And we'll go briefly through these and try to explain them. I'd like you to take out your book and so you can be looking at this graph while we're talking about these, because this is an important graph. We're going to see that the pure sciences are divided according to the 3 degrees of abstraction. The least, the second least, and the most abstract. And then we have ethics, which is the highest science within the applied sciences because it tells you what you should do. And the arts tell you how you should do it. And arts includes everything that you might do, painting, engineering, medicine, whatever that you might do with your knowledge that you gain from up here. And the ethics is in turn divided into these subdivisions: individual, family, social, and political. Methodological sciences include the modes of communications with each other, including logic and linguistics and dialectics, and we'll talk about these. So let's start with the pure sciences, that one at the very top on your drawing. Again, the study of truth as truth. Metaphysics is the first philosophy. Physica, or physics in the wide sense, is a study of all changeable being. It includes within it chemistry, which is the study of non-living substances, and biology, which is the study of living beings. None, note, are yet the sciences as currently practiced. They are practiced in what we'll come to identify as a dialectical mode. They're not the modern sciences as you know them. The modern sciences are pieces inside of these broader sciences. Mathematica, the study of universal quantity, can be broken up into geometry, and in geometry we just leave behind the general and just consider shape. We leave behind the general quantity and just consider shape. In arithmetic, we leave behind all qualitative aspects of shape, and we just are left with number. And analysis is the modern mathematical science that bridges the gap by using beings of reason to connect arithmetic to geometry. For example, a being of reason is an infinite limit, like in an integral, where you take the limit as things go to infinity. And we'll see in another lecture that you can't have an infinite amount of anything, an infinite number of things in actuality. These are beings of reasons. They can't exist except in the mind. And this is the ever-expanding world of Mathematica. Constantly new beings of reasons are being created. new analogies are being made by looking at the real being, mathematical beings that we abstract from the world. The applied sciences are, again, the study of truth and action. And the goal is to conform one's actions to reality. Before, the goal was to conform one's mind to reality. Now we want to conform one's actions to reality. Ethics answers the final cause. That is, what end should we go towards? Others give how you should do that, those particular ends. So this science, the truth and action sciences, cover both the why and how of what we do. For example, again, give an example of how important it is to know what we're doing here, and to first have the higher sciences, which is the sciences that study truth as truth. So for example, this right here is an electrolytic capacitor. And I don't know if you can see it, but there's a plus sign on this side. And what that means is you're only supposed to hook up the plus side of the battery to that side. And if you hook it up the other way, you're not respecting the reality of the nature of the capacitor. And in fact, I had one student who didn't respect the reality of the nature of the capacitor, and during an experiment, he hooked it up backwards. It was actually an experiment as part of a test. And the thing blew up and started part of his test paper on fire. So this is why we have the sciences of truth in action, so that we can learn how to use things according to their proper nature. The methodological sciences, the lowest sciences, because these are used as a tool of the other sciences. Logic, St. Thomas says, this is the one we should learn first, because it's a tool needed for all the rest. Important thing about logic is it is a necessary tool, but it has no meaning except for to bring us to truth in the other sciences. It's a tool of the other sciences. Dialectics, which is a part of this methodological sciences, is probable reasoning based on the use of beings of reasons. And these beings of reasons, as we said, they're beings that only exist in the mind. And so they cannot be used as proof of anything, but they can be used as middle terms to get us to probable statements that in some cases are virtually certain. And so finally we have the use of the word philosophy in the wide sense that we should explain here. And because that's what we started using in the wide sense. We'll continue to use through the course, by the way, philosophy in the modern sense, which is restricted to the first principles of science, of the sciences. Descartes used this in the wide sense that we're using it as well, because he took it from the Middle Ages. And yet he didn't quite use it the same, because he took it as a homogeneous science, not having the distinctions we've shown that are really there. He took everything to have the mode of mathematics. Christian Wolff changed it to the modern usage, which is just the first principles of all things. And in that categorization, we'd have Physica, Mathematica, Ethics, and Logic. And of course, Metaphysics would be the first principles each of the science. Ethics, remember, was the governing science, and then the applied sciences. Logic would be the governing science for the methodological sciences. What about modern sciences? What is their place? Let's concentrate on the so-called hard sciences, and that means the ones that have been most developed. And of those, physics is the most developed. Chemistry and biology are becoming more and more developed, but the science, modern science that started in the paradigm for the rest of them is physics. Modern physics is the unique part of Physica, or physics wide sense, that is what I will call imperial metric. And before we get to that, we'll notice that this can be called a science, modern sciences can be called a science only in an extended sense. It is because it has its own proper methodology that can be kind of worked in its own world, in the worlds of beings of reason, as we'll see, and because its conclusions within that explanatory realm can be justified within that realm to some degree. And they do give some kind of level of certainty about quantitative relations. So we can call it a science, but only in an extended sense, because what we're going to see is that this is a tool. modern physics really is a tool of the bigger science of physica. We need physica to reach real being as opposed to beings of reason. Aristotle recognized this tool, which he also called a mixed science, as one that is formally mathematical and materially physical. That means it takes its material from the world, but it expresses it mathematically. And we call this imperiometric. Why is it imperiometric? Empirical takes it from the world, measures it quantitatively, metric. So imperiometric. Modern physics is the study of changeable being as quantitative. So that is the tool of physica, because it only gives you as quantitative, as measured quantitative, actually. So we need to find out what real being is there. We have to move another step. Before we discuss that more, notice that the ancients had this. In contradiction to what Hawking said, the ancients understood modern science at some level. Newtonian mechanics and general relativity are examples of modern imperiometric sciences. Their material is massive bodies, and their form is the Einstein equations, for example, for general relativity, and Newtonian equations for Newtonian mechanics. In the ancient world, there was a science of optics that still is, but now it's much more broad. The form then was geometry, and the material was light. It was, and for astronomy, which existed, of course, before modern times. And by the way, we should be careful of our use of the word modern, because the men of the Middle Ages were the first to use the word modern. They applied it to themselves. So modern has a kind of equivocal meaning depending on when you live, but we know what we mean by modern. We mean in the last 300 years or so. Geometry and arithmetic is the form of astronomy, but the material is the planets and the stars, or was the planets and the stars for the ancients. So, what do we have? We have the following differences. Aristotle, when he was looking, he probed deeply into all changeable being, or mobile being, if you'd like to call it that, the sensible being this purple stuff here. But he probed past that and deduced the presence of this whole world of mobile being. He also probed past the mobile being into the whole world of metaphysica. Now, Descartes just glanced the surface to get to quantity and just lived in this world. Einstein, he glanced into the heart of this ball, but let his glance reflect up into a small part of the equations and mathematical entities within this preter-real area of the mathematical beings. Most of them being beings of reason, things that can't exist outside the mind. So, the empiriological versus the ontological. There's two different modes of explanation. So, for example, if I looked at, and we're explaining empiriological now, so don't worry if you don't quite get that yet. Insect, for example, if I take an insect, I can ask two questions about it. I can ask, what is it? And I get or I can ask, what, in other words, what is it primarily as intelligible? That's first question. Or I can ask the questions of philosophy, the questions of the empiriological and the logical. And the empiriological then would take measurements. For example, on an insect, I might count the number of legs and then group all the insects with the same number of legs into one category. Now, that might have nothing to do with what the insect is, but it's a convenient way of organizing what I know. The reason we do it, though, is because it might give us an insight later on to what it is. But initially, it's just a category, a being of reason. The category that you invent to do this is a being of reason that may have no existence outside the real world. And the idea is to test and find out, to use this empiriological to come back and answer the four causes. And we saw some of these. The material cause, the formal cause, the efficient cause, and the final cause. Remember, they answer these questions. What is it made out of? What is it? What caused it to be? And what is it for? Where is it heading? Where is its tendency? Those are the 4 questions you'd like to know about a thing. And the point is this empirical and logical? In other words, taking the material that you get from the world, the changeable world, and casting it into the logical, the realm of beings of reason, and seeing what you can come up with. And this is this science here of using categories is called the imperial schematic, because you use schema rather than mathematics. It is not properly, this imperial schematic is not properly a mixed science because of the fact that it's really remember those 3 planes that we had, it's really all within the first plane. The imperiometric is in the mathematical plane and in the physical plane, whereas this schema one is all in the physical plane. And you take things from the higher planes to come up with, the only reason you do it is to bring them down to the physical plane so you have a schema that can somehow reflect what's in there but keep you tucked into the sensible. And that forces you to use beings of reason most of the time. So the subject of both of these sciences, of the ontological sciences, meaning the study of being, the study of what the thing really is, and the imperiological sciences are both changeable being. Both start with sensible being. The ontological, the one that asks what it is, ascends to the intelligible. It ascends to the question, what is it? The imperiological descends to back to the observable. So the imperiological and the ontological are important distinctions to make. This is where most of the modern sciences are. All of them are there, it's just to what degree they are there. Ontological seeks the essence, the form of the thing. So this is really the question you're interested in at the bottom. The imperiological, the essence is replaced by a being of reason, like the number of legs of the insect. So this is an important point because the vocabulary of the two, the words that are used will manifest to some extent the radically different methods and modes of explanation of these 2 types of science. And remember, we only call this a science in an extended sense. This is the main science, the physica, for example, which uses this as a tool to learn more about what things are. But the worst thing that can happen to you is see the same word used in these 2 references and not make the distinction that they must have radically different meanings. Because one is a reference to a schema, the other is a reference to what is. So be careful to notice a word's context, whether it belongs in the imperiological or the ontological will make a huge difference. Physics as it's practiced today now is a little bit imperial schematic, but really when it's imperial schematic it's because it's failed, and that usually means it's something very new that hasn't been brought under control of the imperiometric, because most of physics is imperiometric. And I give an example of Steven Weinberg. When he first started out in physics, the famous physicist Steven Weinberg is responsible for one of the newest theories that's on a parallel with Einstein's theory called the electroweak theory. But when he started particle physics, which is where the electroweak theory applies, he said was so incoherent because there was so many particles floating around that people just classified them. And he almost, he thought this is almost worthless because it was in the imperial schematic stage. And he helped to bring it to the imperiometric stage. Focus in on a particular example, waves and light. Now Einstein, you'll see in the book I have quotes from Einstein and Feynman, Richard Feynman, who's another profound physicist of the late 20th century, late 20th century. And these people were, if there was anybody experts in the imperiometric aspects of light, there was these 2. And they were befuddled about what light was. And Einstein says, I don't know what light is. Anybody who thinks he does, that's just starting out especially, has kind of fooled himself. Why is this? Well, this has to do with the imperiometric nature of the modern sciences. The double slit experiment, the famous double slit experiment, which I'll show you the result of, appears to give the same result as water waves. But it doesn't mean, note, that because something gives the same external output that it's the same internal behavior. We've already seen that in the case of artificial intelligence. The jump in logic comes, you may think, well, this is an obvious jump in logic. How could this happen? How could someone say, because something acts like water waves and you can't see what it's doing, that it is exactly like a water wave? Well, it comes because of the different modes of explanation. The imperial metric is formally mathematical, not formally philosophical, not formally about being. And so if you get in a groove, an imperial metric groove, you can think everything is mathematical, and you can forget that you have to transition. You have to use what your tool's given you and explicitly think about the physica, the wider physics of what's going on. And here's what happens in the water wave. This is a picture of an actual wave that was started by pounding, say, a big long stick here at some frequency. And these are two holes in a barrier. And you can see that kind of from each of the holes comes a wave pattern. And I've reproduced a thing made in a totally different way, I won't get into it, to kind of show you what kind of results you get here. What happens is you get positive and negative reinforcement of those waves, so you end up with a dark, light, dark sort of pattern. And if I were to put a screen where this purple line is, what you'd see on the screen is dark, light, so on. And what happens in the double slit experiment is you do the same thing except with a light beam over here and two small slits, and you get a slit pattern that looks like this, light, dark, just like it was a water wave. We can see in an example of the difference between a double slit by looking at, for example, a problem more easily solved ontologically, and that is, if we look at this rock, for example, you see something here that looks like, you don't know what it looks like a line of some kind. But what is it? You only know vaguely what it is at this point. And it could be a shadow, it could be a marker, it could be an indentation in the rock. And to find out, what we can do is we can take our fingers and we can feel it and see if there's an indentation there. And if that doesn't work, we can take a magnifying glass, try to look closer, and then we can go to a microscope. But notice what's happening here. We stayed very close to our initial senses here, which means you have the most certainty here. And as you move this way, you have less certainty because you're introducing other things. At a magnifying glass, it's pretty easy to verify sort of roughly that the magnifying glass is working. But by the time you get to a microscope, you have some theory that you have to impose to make sure the microscope is accurately conveying what's there. And then by the time you get to an electron microscope, you have a whole thick layer of theory between you and the thing. And so the double slit experiment, you can't just look closer at it, touch closer. It doesn't help you. This sort of directly ontological approach doesn't work. And so you have a totally different level of certainty when you have to resort to that sort of, the electron microscope equivalent over here. And what you have to do is resort to the imperial metric, where you try to figure out what the quantitative the relations between the quantities that you measure are. What we've done in comparing the water wave to a light wave is we've substituted in the same way we did with the blind man and the color red. Remember, he said the color red for him is a being of reason. He doesn't know what it really is because he cannot see it. He has to have a substitute for this by the behavior of the bird, and he says there is this thing red that causes the bird to behave differently in the presence of it. But he doesn't know what it is, but only by way of metaphor. And so we can start with this kind of metaphor that water is kind of like, in some vague way, the waves of light that go through a double slit. But we have other things here. We could check the accuracy to see how closely the wave equation, for example, that describes light, for example, water, also describes light. But even equations can have a more or less probable correspondent to measurements. But we can say in principle fix that. But one equation can describe two completely different physical situations. And you have that, for example, in the electroweak theory, where the mass is introduced. It's a complicated process, but to simplify it, where mass is introduced by way of a certain sophisticated mathematics in mass in particle physics, I should say, is introduced by sophisticated mathematics. And that particle physics mass was first used, the same exact equations that give that mass in the particle physics were also used in superconducting in the solid state physics. Same equations, two totally different physical things causing the quantitative relations obtained. So quantitative certainty can be improved, but the ontological is the problem. What's really happening is unstable with respect to those sorts of investigations. And this is what caused Kuhn to introduce the idea of what's called a paradigm shift. And it all comes about, and he ended up going into subjectivism, because not understanding this distinction between the emperiometric and the ontological, a very important distinction that Aristotle and St. Thomas knew already. But for example, Orsim, Buridan, and Galileo had one set of understandings of the relativity of motion that was based on their emperiometric theories. Orsim and Buridan, not so much emperiometric, but Galileo certainly. And Einstein brought a whole different emperiometric theory that overchanged the ontological interpretation. And the whole reason it overturned it is because the emperiometric was interpreted directly ontological. And we'll discuss that a lot in the rest of this chapter, as well as in the next chapter. We can say the electric field waves, but we do not ontologically know what that really means. It's an emperiometric statement, a mathematical statement that we have to find out what real beings are causing. Now, as you increase the complexity of a theory, more and more beings of reason get introduced, and it becomes harder and harder to find out what's really underneath causing the things you see. Again, just because you're convinced of the quantitative relations among the measured quantity, i.e. a set of equations, it doesn't mean you've explained the thing ontologically. And for example, if you approach the light from one aspect, it appears to behave like water. From another aspect, the quantum mechanical aspect, it appears to behave like a billiard ball. So if you take each of these emperiometric statements as ontological statements, if you say, well, light, I know what that is, it's just a wave. It's the same as water wave. Well, then that means it's spread out all over the place. But then if you take the quantum mechanics, the emperiometrics of quantum mechanics, and you say, well, I know what that is, it's a billiard ball, it's right here. Well, then you get a contradiction, because you say the same thing is both just here and also everywhere else, but really not, it's just here, not everywhere else. It can't be both those things, because that, again, is two things that, I mean, it's a violation of the principle of contradictions, that something can be and not be at the same time and in the same way. The lesson here is modern emperiometric science does not give us an ontological reality directly. This means we've got to take care in understanding our equations. It doesn't mean we never can get to the ontological from the emperiometric. It just means in these extreme cases that we cannot, which is where modern physics is at now. It's really out in those extreme cases. But in the more minimally emperiometric theories, you can. Matter of fact, a almost directly ontological one is what St. Thomas says. Again, if someone didn't believe that the medievals knew the earth was round, here's a perfect example of a proof that probably most haven't thought of. And St. Thomas says, for example, that you can deduce that the earth is round by looking at a lunar eclipse. Because what is a lunar eclipse but the earth blocking the sun, and it leaves a curved shadow on the moon, thereby leading St. Thomas to say the earth is round. So these are very close to the sensible. So we can do that with that kind of emperiometric. But when you get deep into the emperiometric, where you have lots of beings of reason, it's much harder. But remember, the real being is present as a remote or proximate foundation, is responsible for the stable relations that you see either in the emperiometric or the imperial schematic. The emperiometric is basically revealing the underlying quantitative unity in some hidden way. You know, it reveals as much as it obscures, is one way of saying it. But at bottom, there is real being causing the profound interrelations you're seeing, of course. Some real being rises to the surface. Over time, some of these are atoms, electrons, protons, neutrons, and quarks. And as you start from the left to the right, you know, there's decreasing certainty. These are virtually certain, and these are highly probable, very little doubt. What are they? That's a different question. We'll get back to that. But the fact that they are is virtually certain. And this requires something that's very rare today, and that is philosophical knowledge and knowledge of modern science. In order to take the empiriometric or the imperial schematic results and understand what they mean, you first have to know what the empiriometric results are and then convert them back. In our society, you find very little of the philosophical knowledge, but you find it's almost a complete rarity to find knowledge of both these, which is what you need in order to bring these things to clear understanding. And this explains why we have to be even more vigilant in our thinking about these things, because it's not been done much. So the mistakes are going to be made more and more often. Without this knowledge of the science before science, what happens? Well, Kant started this experiment very early on. He really codified the philosophy that you get when you take everything as empiriometric. When you take modern science as the rule of thinking, this is where you go. And he basically, I call it a lived Godall's theorem, because he basically proved that if you do this, you're going to close, this is the suicide of science we talked about at the beginning. He tried, what did he do? He was very enamored with Newton's theory. He didn't understand it really, but he was enamored by it like a lot of the humanities people at the time. Not unlike a lot of the humanities people of our time of science that they don't know. But remember, empiriometric theory has no certainty about the ontological. Only physica can give that certainty. Well, Kant didn't realize this, and this caused him to become a philosophical idealist. Beings of reason were the only thing he thought he knew, because remember, the empiriological lives in the realm of the logical, of the beings of reason. And thus he came to the idea that no one can never know anything. And this he did because he tried to take Newton's theory and give it a certainty that it did not have. Indeed, this is when he came up with this idea that the only type of geometry that the mind of man could ever conceive was Euclidean geometry. And Gauss had to fight this, because it wasn't too long after this that Gauss came up with non-Euclidean geometry, and he was afraid to publish because of the error in the world created by the Kantian philosophy. So it is very easy to forget the nature of empiriometric knowledge. By long habit of using it, one begins to think that it is everything. And you have to remember that when the empiriometric, you're using the mathematical, and you've left all those things behind except those things that are quantitative. And so you deliberately did this in the beginning, but later on you can get confused and forget that you've done this. And it's just like staying in a dark room all day. You get habituated to the dark, and when you walk outside, it takes you a while to get re-established. Well, you can imagine if you've lived your whole life in the empiriometric, or some large part of your intellectual life, that you'll be very confused. And some examples are that talking to some of my colleagues, for example, about these things, talking about the idea of change, he immediately connected it with the idea of a time derivative. Well, a time derivative is a mathematical concept that describes change. It's going back the wrong way. It's starting from the empiriometric going to the ontological, where in this case, we know the ontological fact of change. That's what leads us to think about the description of it that the time derivative is. The time derivative, by the way, is what you get when you take, you figure out what the rate of change of some variable, for example, the rate of change of distance, or the time derivative of distance is the speed. Another person who was very much into the sciences told me that, well, look, electric and gravitational fields are immaterial, which of course is starting from the empiriometric, because as metric things, as mathematical things, they are indeed immaterial. That is not material. But as things in the real world, they've got to be material, because the changeable world, these things that are primary things that make things happen in the world, are changeable. And so this saying that the primary things in the material world are immaterial is nonsense, but it happens because you forget what the empiriometric science is. And this even happened to Newton. When Newton came up with his theory, Newton was much more clear than some of his contemporaries and than most people now. He explicitly said, he got confused himself, but he explicitly said that he was trying to lay out what basically amounts to a mixed science, and that is trying to be formally mathematical and leaving behind the material causes. But nonetheless, he had to introduce one material cause at least, and that is gravity. And he was criticized up and down by the Descartesians of the day, the Cartesians of the day, the followers of Descartes, because he introduced an occult quality. A quality, not a quantity, and occult because you can't see it. Where is gravity? I don't see it. Newton's reluctance to publish was related to things like this. When he first came up with these things, they lay dormant because he didn't want what he said about the ignoramuses to make objections to his theory. So again, if we keep this confusion about the difference between the empiriometric and the ontological in mind, we can understand things, and there's a proper place for the empiriometric and a proper place for the ontological, and we've seen what they are, but we have to keep them in place. If not, we can lead through mathematics to a philosophical idealism, which basically ends in subjectivism because you're stuck in your head and you can only know yourself then because you can only know your ideas. And this leads you to Godall's theorem. Because once you try to stick in your head, the first thing you're going to try to do is what Godall did, which is try to say, look, I'm concerned about truth, so I'm going to prove that within a system of ideas, I can prove everything within that system. And he was devastated when he found out that he couldn't. But mathematics is not the problem. We already said that how St. Thomas points out in the Middle Ages that mathematics is the most connatural to us, meaning the most resonant with our nature. And why is that? Well, we have enough information to say why it's the most resonant with our nature, why it's the most connatural for us. And obviously something that's connatural for us can't be bad. It's just, that's what it is. And we have to make sure the limits of whatever we're talking about and put it in its proper place. Man's intellect knows by immaterial ideas, but he constantly accesses images which he uses to abstract the ideas as well as a crutch for his thinking, as well as to check his thinking and help his thinking along. Mathematics involves both of these. Remember, mathematics resolves its conclusions, verifies its conclusions in the images, by way of phantasms. But mathematics also uses the abstract. So we get to use both areas of our nature and in a way that doesn't exclude images too much, but yet allows us to still use our abstractive powers. Now, mathematics is abstracted from real changeable being. So it is no surprise that it can be used to understand that real changeable being. Remember, quantity is the first accident of all material things. So when you strip away all the qualities and everything underneath, you have extension. So it's no coincidence that what Wigner called the unreasonable effectiveness of mathematics is a reasonable effectiveness of mathematics. What is amazing about it is the mathematics reveals a striking order and harmony to all things in nature. And this is really, I think, what Wigner is getting at, is that he's amazed at the structure of things that look very trivial turn out to be profound and have profound beauty, even in the equations, even in the mathematical aspects. Now note that the less a material thing is, the more it will be amenable to being understood by its first accident. So the less something is, the more it's closer to that primary thing, which is the prime matter or just the extension of the thing. And so therefore it's going to be most accessible to mathematical techniques. And this is why physics works so well, and why chemistry and biology work much less well when they try to be mathematicized, and psychology and so forth hardly work at all when they try to be mathematicized. Because the more being that it has, the more remote it is from its first accident. The first accident is still there, and so it's still going to be amenable to the empiriometric method. It's just less easily done. So mathematics is a danger for physics. And mathematics and the mechanistic thinking that go with it is largely responsible for both the cause and the success of modern physics and its vulnerability. The success, of course, is the powerful understanding of material beings at a certain level and in a certain mode, in this quantitative mode. The vulnerability is to make the mistake of thinking that because of its ease and power, because it's easy for us, that's all there is. I mean, it's a temptation we all have, is to do what we're good at and exclude all else. And whatever we're not good at, of course, is not worth doing and is not an important part of reality. But of course, we all know at the bottom that that's not true. We could be really horrible at something, it could be very important. And so we have to be careful, because this one is so connatural to us, that to not let it rule as the only mode of explanation. What is more results of thinking like Godall? Well, thinking like Descartes. Well, we said that it can lead via Godall's theorem to doubt truth, because you become an idealist and you get locked into Godall's way of thinking, and you find no way to ground yourself. The other thing is that mathematics is a small world. It has minimal material causality, because you've excluded quality and all these other things. It has no efficient causes, no motion. And this can cause a lot of problems. It can cause the inability to recognize the difference between act and potentiality, for one thing. And how does this come about? Well, you've probably all seen this in your freshman physics courses, or in even your high school physics courses, where you draw a picture like this, where you have time on this axis and distance on this axis, and you say, there's a ball moving across the room from left to right. It starts at some position at 0 time, and then I throw it and it moves, or I say it's a billiard ball and I hit it, and it moves to the right. And as time goes on, it advances in distance from where I hit it. Well, notice something interesting about this plot. The ball moved from right to left, but on this plot, everything is at the same time. The picture is all at once. There's no potentiality and actuality. In the picture, everything is actuality. It's not what motion is. Motion is the process of the reduction of potentiality to act. And this is not. This is actual. The ball is on the right and on the left simultaneously, because this picture is one. What we've done is we've reduced time to being like a space variable. After all, this is the same as this. They're both space. So we have to be careful with these pictures. It's not that these pictures aren't useful if you think of them right. It's just that if you get hardened into an attitude and forget what you've abstracted away, then you can think this is all there is. And you can lose the whole concept of potentiality, which is so important in resolving what already Aristotle did in resolving the problem of Parmenides. And this is a tendency of people involved in mathematics, is to reduce everything to actuality, like Parmenides does. There is formal cause in mathematics. There is a difference between a square and a rectangle, or in a circle, and so on. But it's a very narrow formal cause. It doesn't include very deep things, because we're just dealing with the first accident of things. There is no final cause whatsoever, because there's no motion. And as a result, there's no good or evil except by choice. I can say, well, look, I really like this mathematics because it helps me to describe how a spacecraft might go to Mars. But it doesn't mean that mathematics in and of itself is good. It just means that I like it, because I like to go to Mars. So it's a choice. And what this can do is lead you to think that all things have this choice aspect, that I sort of choose the way the world is. Because within the mathematics itself, there's no good and evil. So you pick these things for a reason exterior to the thing themselves. I don't pick the calculus of going to Mars because it's the calculus of going to Mars. I pick it because the calculus within the calculus, it has nothing to do with Mars. But the calculus itself is an accurate description. And so I like it because of that, not because of the mathematical elements and contain something intrinsic about Mars. And this can lead to what a friend of mine said, there are no categories. I can put anything in any Macintosh folder I want. He might say, I can put, birds in a red folder, and I can put roses in the red folder. That's just because I choose. But of course, That's the whole point. The empiriological leaves behind what the thing is and just looks at categorizing its sensible qualities. Of course, we know that red is not an essential aspect of a rose. A rose can be white or yellow. So we can choose to put it in red, but that doesn't make it be red, but be an essential quality of a rose. But why does this happen? It happens because of a mathematical bent in our culture, habitual use of mathematics, even by those who don't practice it. In the culture, there is the leaving out of the final causality. You don't have the natural thinking, the final causality, because of the prevalence of the mathematical, which itself, being quantitative without the rest of the accidents, leaves that final cause out. One thing is this, what I call serial thinking. In counting, each step is just like the next step that came before. No difference. No qualitative difference. But for example, one person said to me about intellectual knowledge, why couldn't sensorial knowledge just get bigger and bigger and bigger until finally it was intellectual knowledge? Well, this is a mistake of serial thinking. It's forgetting that some steps are qualitatively different than another step. And this, for example, the difference between a sensorial knowledge of something, a knowledge of the particular by way of phantasms, is an infinite jump because of the fact that the general and the specific are infinitely distant from each other. So once I make that first abstraction, if I get higher and higher sensorial knowledge capabilities, once I get that first abstraction, no matter how small it is, I've entered this new world of being able to understand things in a general way, in a non-material, purely non-material way, independent of the material. And so already I have the active intellect, and the qualitative leap has been done. There's no more to do. It's similar to the story of an Irish legend of a woman, and I'll modernize it, of a woman who decides that her heating bill is too much because she has to use very expensive wood that's around her house, and she can get more money by selling it and to heat her house. So she decides to buy a modern heating system and puts it in, and she discovers this cuts her heating bill in half. And so then she says, hey, I'll go get another one, because she said if that cut it in half, this will cut it in half again. Serial thinking. One step is qualitatively different than the other. Another one is algorithmic thinking. Because of the non-changing nature of mathematics, one can make procedures to do things. You can make software and just do a bunch of steps. This can lead to automatic thinking, to not thinking about what things are, but just doing a set of rote actions. For example, when I was a kid, I learned the truth table for geometry, and it was just a set of TFs, and it had no relation to true understanding of what it meant. I was just taught that TF means false, and all else means true. And you know, that has no bearing, and you can program that into a computer. So algorithmic thinking is important, but this sort of manipulation of beings of reason that comes out of this sort of blind automatic manipulation can lead one to categorize all things as being of that type. Beings of reason, again, is another area where confusion between them and real being happens. And we gave an example of light. Light is an entity, but if you think of dark can be the absence of light, or light can be the absence of dark. That's if you think of both light and dark as being beings of reason. But in fact, light is a real being. What is dark? Dark is the absence of light. So dark is a being of reason. Dark cannot exist of itself. If here's a dark, well, there's no dark there. There's the absence of light, but dark of itself cannot exist. For this reason, a man who's born blind doesn't know what dark is, because he doesn't know light. Light is what defines dark. It's the absence of light. This is what comes from mathematics and thinking in terms of beings of reason and giving everything a being of reason sort of categorization rather than making this distinction between real being and a being of reason. All these dangers come from mathematical thinking. You don't have to be a mathematician to have these things. You just have to be in our culture where these things are given the emphasis. and these other things are not discussed. Chemistry tends to be still imperial metric, but also tends toward the imperial metric. By the time you get to biology, the concepts are largely imperial schematic. And that, again, has to do with the fact that you're moving from lesser beings to greater beings, and that first accident, which is quantity, is harder to access because you have other layers on top of them. We see that the issues here are complex that determine the interplay between philosophy and modern science. Philosophy, narrow sense here. Now we have the background to understand what Hawking was saying, and you can see why these confusions can happen. Anything with this sort of level of complexity is going to cause people to fall off the edge one way or the other. Hawking's first question then, is modern science radically different than anything that came before it? Yes, it is, only if one removes the word radical, because and uses significant, because Newton's theory was really the first fully empiriometric theory. It is only with Newton that all elements of empiriometric theory are brought under one predictive umbrella. But in the real sense, the answer is no to what Hawking said, because Aristotle and Galileo actually was educated and so was the whole school that brought Galileo to being educated in Aristotle. And they knew about how to do these things because Aristotle taught them first in St. Thomas, and the rest brought them to them via the schools. So in the real sense of the word, they knew about the modern sciences. It's not radically different. It's just a matter of degree. Why the conflict then? If the empiriometric science was there and philosophy was there, why the conflict between the empiriometric and philosophy? Well, many promoters of modern science, especially in the humanities, did not understand the empiriological nature of the methods and treated them as pure physica, treated them as pure philosophy, thereby confusing the real with the schema and the equations that were presented in the empiriometric. So this caused them to disrespect those who remembered real being. So those who remembered real being were looked upon with scorn because they were still talking about things, looking for the essence of things. Another thing is that Aristotle and St. Thomas had different strengths and different interests than most moderns did. Now we're talking around the time of Galileo when we're using modern now. But it's also true of us. The mathematical interests weren't there as much. The interest was more in what things are. And particularly Aristotle was interested, as we saw before, profoundly interested in biology. And the mathematical aspects we've already seen, apply to biology as easily. And similarly, St. Thomas's teacher, Albert the Great, also a great biologist, was not as interested in the mathematical end of things. Aristotle's, and St. Thomas's interest was more in theology as well. Both, of course, I want to emphasize, did make important contributions to physics nonetheless, physics in the modern sense. Aristotle, because of errors in his theology, not in his philosophy, we'll see that later, this has to do with Aristotle's cultural milieu, had to have things softened by St. Thomas. You can't expect these geniuses, after all, to do everything. But the basic bottom level, science before science, was in place by them. Rote Thomism set in some places, but it wasn't absolute because you already had Theodoric discover the fundamentals. Descartes basically perfected it and came up with the total right answer, but the fundamentals were done by Theodoric. Theodoric had this sort of mostly complete idea of how to calculate the rainbow. He's a Dominican follower of St. Thomas. So we must conclude here that some of these things here need a sort of a seeding to come to fruition. And this seeding is, I will contend, is a deep-seated prejudice against Catholicism. Because Hawking claims the Catholic Church is or was intrinsically opposed to science. If we can show this is not true, we have grounds for our charge. Because after all, you're talking about an institution that is worldwide and knowledge of it is easily accessible, and he's a well-known, respected physicist who you would expect someone to correct so that he wouldn't look foolish if there weren't some sort of built-in bias in the culture that automatically nods to these things. And we see Hawking's charge is clearly false. Galileo himself was a devout Catholic. It's part of the reason he got into trouble, because he tried to reconcile some of the things he was saying, and he didn't do it in the most, what shall we say, graceful manner, or in the most humble manner. But the fact is that, and of course people know by now, but since the book Galileo's Daughter has been out, that Galileo's daughter was a devout nun, who they wrote on their beliefs often to each other. The Carmelite nun, which is a very austere way of living. But the question is, can anyone really believe that the beautiful flower of modern science would come to fruition in the only part of the garden that's poisoned? Because after all, it didn't come in Egypt or China or undiscovered North or South America or Japan or anywhere else. It came right in the heart of the Catholic Church. So already accessible to sort of easily found history, we can find out that what Hawking says is patently untrue. So, in other words, we would be saying that we and everyone else receive from the poisoned garden all these truths of science. Actually, this turns out to be the well-kept garden. Such cultures include a certain thinking that promotes science. And this includes non-Catholics of all sorts that have been passed this information. This information is the general sort of thinking of a culture that everyone accepts as true to some degree or another. Here are some of those things that were handed down, and this is not common. This is uncommon except in Catholic cultures or Catholic-generated cultures. That is that the world exists independently of us and is orderly. 2, that we can understand it. And 3, that we should have no aversion to working on it because it is good. This is the experimental side. And 4th, we'll see later, the non-necessary character of the world is also enculturated in the Catholic culture that is passed on to non-Catholics, even atheists as well. Accept these things, they don't know why, but it's the improper knowledge that we talked about, like we have of the earth going around the sun. One of the most quoted verses in the Middle Ages was the Catholic, of course there were Catholic ages, was God has ordered all things in measure, number, and weight. And showing that the respect for the order that the medieval man had. Of course, the Christian culture always inculcates the dignity of man, and especially his ability to reason and understand creation. The very famous historian Lynn White sums this up very well. For the first time, he says, and he's talking about the beginning Middle Ages now, starting right after the fall of Rome. For the first time, the practical and theoretical were embodied in the same individuals. In antiquity, learned men did not work, and workers were not learned. The monk was the first intellectual to get his fingernails dirty. In his person, he destroyed the artificial barrier between the empirical and the speculative, and thus helped create a social atmosphere favorable to scientific and technological development. It is no accident, therefore, that the friars were eminent and ardent in experiment. The experiment is brought home by the first part of Genesis. It said, and God said it was good. The incarnation, of course, takes this and makes it irrefutable for the Christian that if God could become man, the world must not be bad. This is the Christian belief, that God became man. Renowned physicist Pierre Duhem basically rediscovered the medieval foundations of modern science, and that Galileo had taken most of his ideas and brought them to fruition by standing on the shoulders of giants, and those were medieval giants. And he was shocked to find out as he started studying the history that the medieval roots, and he has 10 volumes still only available in French. A modern secular historian says that, and very succinctly, modern science is a child of medieval science. Hence, we come to the conclusion that Catholicism is not inimical to modern science. Indeed, we should be careful because our modern culture, at least in the area of science, has something in it that tends towards saying things untrue about Catholicism. It's important to check our improper knowledge here And this is the reason we go into this whole thing of the issue of whether the Catholic Hawking statement about Catholicism is true or not, because we need to know whether that improper knowledge that we're getting is going to lead us in the right direction or wrong, especially about a force like Catholicism that's responsible for the first universities. Almost everything in our culture has some roots in the Catholic Middle Ages and back before that. Hospitals, law, music, respect for the human person, worship at various degrees. If it is wrong about science, we better know it. Is Galileo largely responsible? Again, we said that's only true if qualified by the fact that, as Newton said about himself, that he stood on the shoulders of giants. We must say that about Galileo. And we'll talk about some of those people. Among them is Copernicus, who properly belongs to the Middle Ages. But we'll talk about some of the ones that people have heard of less in the next lecture. Galileo versus St. Thomas then is a red herring. Indeed, they contribute to each other. Should be rather Galileo and St. Thomas. Modern science and philosophy are not opposed to each other. Indeed, we saw the philosophy is calling for modern science. And we need modern science to help fill out in the areas that we don't understand. But they can't come backwards and destroy the base that's calling for them that they build on, because then we destroy them as well. So the ontological studies, the philosophical studies, if you want, use the empiriological. Modern physics, mathematics and measurement of the empirical is called emperiometric. But it's important to see how this verse is arised in the first place to keep ourselves from falling into the trap of listening to sources of improper knowledge that are not faithful, I should say.